Hi, this is Dan Bullard, retired electronics engineer, sitting on the Fettica mouse. But again, it's July 5th, so the weather's improved a lot. So this is part 3 of the Nextest DSP training course, and I'm trying to get through it in a reasonable number of episodes. So let's get into non-coherent sampling. I talk about non-coherent sampling a lot. That's what you do when you use a scope. So sometimes, we just talked about coherent sampling, sometimes you can't sample coherently. Noise, power supply hum, switcher noise, asynchronous sources like oscillators, intentional or not, like parasitic oscillation, free running DUTs. I had to test a free running device one time. It was a pretty interesting device, and I needed to test it and measure the duty cycle of a free running clock. That was pretty wild. If you can't sample coherently, you can still test it, but you may have to window the waveform. Now here's an example. This one is a 1 megahertz sine wave. The sample rate is 3.3 megahertz, which means that M is not an integer. It's never a good thing when M is not an integer. M should always be an integer if you can do something about it. But this is non-coherent sampling, so you can see that my individual data points, I got 16 of them. You have 0 degrees at 0 volts. You have almost 1, almost 0, almost -1, almost 0 again, almost. You can see they're kind of drifting around, but that's not a solid coherent waveform because the M is 4.875. That's a problem. So if you use that, the signal analysis routines assume that the ends of the waveform will line up if repeated. In a non-coherent waveform, they don't line up. So what happens is the waveform is assumed to be continuous. And if it isn't, then it looks like it has this big discontinuity in it. Windowing reduces the effects of non-coherent sampling by attenuating the end of the waveform. What the signal analysis software can't see, it can't assume. The trick is to gently taper the ends of the waveform so the taper doesn't create another discontinuity. There are a lot of windows available. Now, some would say that a normal coherent waveform is windowed with a rectangular window. That's, it's like saying, oh, this number is not just a number, it's the number times 1. Yes, a number times 1 is itself. A waveform times a rectangular waveform is itself. That's not really, these guys, they try to obfuscate all the time, try to make you think it's really, really hard to understand. It's not. Okay, so here's the time domain waveform again. The SNR is 9.8651 dB. That's really bad. Now, we go off and we generate a Blackman window. Now, how do you do that? There are a lot of ways to do it. I'll show you in a minute. But you can go to Wikipedia. Wikipedia has a list of all the windows that are currently in use. And it gives you the formula for every one. So if you want to, like in Excel or whatever, you can generate your own window. This happens to be a Blackman window, named after a guy named Blackman. So, you could end up, if you come up with a really great window, you could end up getting your name out there. So that's a Blackman window. The idea is to taper the ends. And so what we're going to do is we're going to take that waveform, we're going to multiply it by the Blackman window, and it'll taper the ends of the waveform so that the discontinuity won't be seen by the FFT. So when I window the wave, the SNR goes from a miserable, terrible number to 57 dB. That's pretty good. That's pretty good. Before it was like 9 dB. So it really helps, but it doesn't really, it's not really legitimate, I'm sorry. Okay, rules for non-coherent sampling. Set the sampling frequency as close as possible to a coherent frequency. If you can do that, that really helps. And Daver had a rule, if it was close enough, If you're very close, it'll look coherent. You won't even notice any difference. So you can get really, really close, and there's a couple of ways to do that. So you can sample it at some non-coherent frequency, get a good estimation using the Bunneman function to try to get the right frequency, then sample it again at a closer frequency, and maybe get it coherent enough to give you good results. Okay, the big step there, remove the DC offset before you window. That's something that professor from Scotland didn't know. Glasgow, Scotland, the guy in the UCLA course, I talked about that. He gave a class on DSP, and I asked him about that. He didn't know that. So that's something you should do immediately. So you take the waveform and you do a DSP mean on it, get the average, subtract whatever the average was to get it to be 0. So have an offset of 0. Then you can window it. Don't window it before you do that. You'll regret it. Because windowing smears the DC, causing even more problems. And then in Nextest land, Daver came up with a function. I'm going to talk about Daver a lot. Dave Reynolds. Use the waveform apply window to apply the window. Multiplication does the same thing, but a waveform apply window does an additional step for you. So Daver, he did some brilliant work on this. Brilliant. And it's too bad it's all gone, I'm sure. Daver did all this stuff, and he's, like I said, he's brilliant. Now, I came up with some pretty cool things, but Daver, he's like unbeatable. Okay, Nextest waveforms. Now, you guys are not going to be using Nextest waveforms, but if you end up working on something with waveforms, this gives you an idea of what's required and the way things really work, and it makes it concrete for you. This is digital signal processing. This is what you do. You work in waveforms, and this is how Daver did it. Now, you know, you could do worse than learning about what Daver decided to do with waveforms. Okay, Nextest waveforms are actually C++ objects. I learned a lot about C++ from working on Daver stuff. The type is automatically declared for you. Waveform objects contain more than just waveform data. That's a biggie. Body code for the waveform object is executed during initialization. So that was a really cool thing. C++. I love C++, but most of it I don't really get. You know, I didn't really use it enough. Oh, there's a boat. I think that's the Boo boat. So, objects in C++, let's just say it gets really interesting. Just believe it, okay? So the body code in the waveform object is executed during initialization. It speeds up program execution by generating waveform before testing begins. That's a big deal. You don't want to waste your time while you're testing a part generating waveforms. If you can generate the waveforms before you get started and then just keep those in memory and run them again and again and again, then you save a lot of time. Because remember, we're trying to get, you know, one of the test programs that I did for analog devices, it was a quarter of a second to test a chip. So yeah, you want to get all this stuff done right away and get it out of the way. Okay, declaring a Nextest waveform is easy. You say waveform, ADC wave, or whatever you want to call it, whatever name you want to call it, and then open brace, close brace, that's it. It's an uninitialized variable. It doesn't have anything in it, it's just a waveform. But the body code and everything else has been set up for you, so now you can do it. Now this is the kind of stuff Daver did, okay, when he was working on the STS 3000. We wrote that in Pascal. All that code was in Pascal, but it wasn't really Pascal. They were taking the Pascal code and turning it into C. That was behind the scenes. So the stuff that Daver did behind the scenes was brilliant. So waveform object, it's got a whole lot of stuff in there. It's C++, it's got a whole lot of stuff, and just believe it, it works amazingly well. Okay, there's 4 waveform types, and that's a biggie because I've talked about some of these types. There's an R-rect wave, which is a real rectangular wave, basically an array of doubles. Doubles meaning double precision floating point numbers. There's an R-long, long rectangular wave, basically an array of longs, 54 bits maximum. So these are integers. C-rect wave, which is a complex rectangular waveform, basically it's an array of 2 doubles, one real, the other imaginary. Now, being imaginary, it doesn't mean it's not real, it's really there. And then a polar wave, complex polar waveform, basically 2 arrays of doubles, one magnitude, the other phase. The R-rect wave is the most often used type. This type generally is used to represent time domain waveforms that may be loaded into the AWG or read from the ACI. Time domain waveforms are indexed by time in the x-axis and contain voltage or current information in the y-axis. The x-axis values are fixed in time by an increment. The first value is set by x start. So here's an example, and this is from the file. So when you save a Nextest waveform file from the Nextest, it goes into this type that you can look at. You can actually go in and edit if you want. So this is a Nextest waveform file created Wednesday, February 12th, 2003. Boy, that was some time ago. Near the end of the day, too. Okay, name is 16-point sine wave. Could be anything you want. X increment is, that's 1 over the sample frequency. X start, 0 seconds. That's 0 seconds in this case because the X units is seconds. Y units is volts. The type is R-rect. That's how the waveform is separated from the other types. And it's got 16 samples in it. So that's N. That's the number of samples in the waveform. And there goes 0. Let's see, have we seen these numbers? 0.383, 0.707, 106, blah, blah, blah. 0.923, yeah, we've seen these numbers before. So this was from our 16 sample sine wave. And it goes on and on to the very end. Now this is kind of cool because these waveforms can be read by all kinds of things. It's not a bad way to go. You can create waveforms this way in Perl or whatever and then read them out. It's a really nice way to go. Okay, then there's the R-long type, which is generally used to represent time domain waveforms that contain integer values. Values in R-long wave are limited to 54 bits. Uses for this type include input to a DAC or the output from an ADC. These are generally time domain waveforms. But another common use for this type is to store histogram data for testing ADC linearity. And I'll be showing you that. I'll be showing you ADC linearity a little later. Not today though. So here's an example of an R-long waveform. Nextest wave file. Created blah blah blah. Getting closer to the end of the day. 16-point R-long sine wave, that's the name of it, but it can be anything. X increment is, that's the 1 over sample rate. X start is 0, X units is seconds, and Y units is volts. Type R-long. Now these are all hexadecimal values, 16 samples long. Basically these are the same values that we looked at before, but they're rounded into integers. So 080 is that's the 0 point, and B0, I'll bet you that's the 0.383, and so on. So those are R-longs, and you use them for ADCs mostly, anything where you have to have an integer, but it's only 54 bits. The next one is a histogram. So it's an 8-bit histogram. X increment is 0.996 blah blah blah. That's in volts actually. X start is 0.498. X units is volts and Y units is counts. It's an R long. Now I'll get into this later. I don't want to get into histograms right now, but this is something else you can do with an R long waveform. Okay, the next type is pretty interesting. It's a C-rect. That's complex rectangular wave. It's a two-part complex waveform that stores frequency domain data. These waveforms are seldom used. Usually just convert them to polar. Now there are exceptions to that, but waveform filtering should be done as a C-rect waveform, however. So if you want to filter things, you should do it in rectangular form. It's much harder to do it in polar form. And trust me, I know what I'm talking about. So do them in, if you want to do filtering, do it in rectangular format. The two parts of the waveform contain real and imaginary parts corresponding to cosine and sine amplitudes. So here is a waveform file. It's a C-rect wave, that's what it's called. The X increment is 333.3333 hertz. X star is 0, X units is hertz, Y units is volts, type C-rect, size is 9. Why 9? Well, because it's probably an FFT on 16 samples. And so here we have two parts, right? 4.8 blah 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 and 0. 1.0. Look at the next one here. 0.707, 0.707. That is the fundamental right there. That's the fundamental. So it's in sine and cosine amplitudes. Okay, the next one is probably much easier to understand. Polar wave type is a two-part waveform that stores frequency domain or spectral data. The two parts of the waveform consist of a magnitude part and a phase part. The phase part is in radians. Since the FFT function returns a C-rect wave, you need to convert from C-rect to polar to see polar data. Normally you want to see these things in polar. C-rect is really not very helpful, but you have to go through the process to get to see from C-rect to polar. And we'll talk about that. Okay, so here is a polar wave. I call it that. The increment is again the Fourier frequency, that's 333 hertz. It tells us that in the X units. The Y units is volts, type is polar, and the size is 9. So that's n over 2 plus 1. And so that was 16 samples. Divided by 2 is 8, plus 1 is 9. 1 for the Nyquist frequency, which again you never use. Okay, so this is this value, 4.8 blah 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 times 10 to the minus 16th and 0. That's DC. The next one is 333 hertz. The next one is 666 hertz. And the next sample is 1 kilohertz. And it's got a value of 1 for the magnitude, and the phase there is in radians. Okay, rectangular versus polar. Rectangular form describes point in terms of lengths and directions of two sides of a rectangle. The polar form describes a point in terms of the length of the diagonal line across the rectangle and the phase angle. So it looks like this. So here we have rectangular 0.707, 0.707, and the polar is the length of the hypotenuse and the angle. So that's what polar means. Okay, let's talk about generating waveforms. Waveform generates sine wave, generates a sine wave. These are functions in C++ that you would call up. David wrote these. Waveform generate ramp, generates ramp wave. Waveform generate triangle wave, generates a triangle wave. Duh. Waveform generate square wave, generates a square wave. Waveform generate DC, generates a DC level. And these can all be used together. Waveform generation routines, noise. You can generate Gaussian noise, you can generate white noise, you can generate periodic white noise, you can generate periodic pink noise. You can reset the random seed, so if you want to generate noise, you can reset the seed in the random number generator. That's a really cool thing because it means that it's not really random. If you set the seed, then it's always the same sequence going on in the future. So if people freak out, because you're doing random stuff in your test program, you can set the seed and then it's always the same. So it's never ever going to be totally random. And then there's a function called waveform randomize. Okay, so here we're going to generate a sine wave. Okay, so waveform generates sine wave object. That's the thing that we're going to generate. 512 samples. There's a sample rate, 24 megahertz, 1 volt peak, 0 volt offset. The waveform will be 1 megahertz with a 1.57 radians phase offset. So that's how you do it. So you generate a sine wave there, boom, get a sine wave. So this function does all the memory allocation and waveform generation and everything, so you don't have to worry about it. It's really cool compared to the Vista, okay? So this is Daver writing code for the Nextest, and it came out so good. We had so many bad examples from the Vista. The Vista was C, it wasn't even C++, so it was terrible. Okay, now you can generate waveforms or you can save them. So once you generate a waveform, you can save them. Waveforms can be saved to disk and retrieved from disk. So there's a Boolean function called waveform read file and Boolean waveform write file. So then you can say if not waveform read file, blah, 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 top 10 wave, N wave, it's called N wave for Nextest wave. That's pretty cool because the if statement goes out there and looks to see if the waveform actually exists. And if it doesn't, it returns an error. But if it does, it reads the data into the waveform from the file and then you're good to go. It's a really nice thing. So if you find something interesting, you can save it to a wave file because it's just a text file. You can go in and play with it. You can print it out, you can read it, you can fiddle with it and put it back. You can read it back in. It's really cool. Okay, here are some waveform functions, really simple ones, simple DSP functions. So waveform add, waveform outwave, waveform inwave, waveform inwave 2. So that adds inwave 1 to inwave 2. Pretty cool, right? But it also works this way: waveform add, waveform outwave, waveform inwave, double scalar. And then waveform add, waveform out, waveform inwave, double scalar 1, double scalar 2. So that's pretty cool. If that were a complex wave, you could add in 2 scalars. So it knows what it is. It knows what kind of waveform it is. Here's another one. Really simple. Waveform generate sine wave temp 512 blah 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 blah. Waveform generates sine wave temp blah 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 blah. So it's a 2.9 megahertz wave and a 1 megahertz wave, and then you do a simple waveform add. It adds the 2 waves together. What does that make it? That makes it a multi-tone. So you can do a multi-tone test and see if it has a problem with 2 tones. Subtracting. So you can say waveform subtract, in wave 1, in wave 2, or waveform subtract, waveform outwave, waveform in wave, double scalar, so you can subtract something. So for example, if you want to remove a DC offset, this is how you do it. Waveform subtract, outwave, waveform in wave, and double scalar 1, double scalar 2. So if you're trying to do a complex wave, you can do that. Now here's an example of multiply. Waveform multiply, so you can multiply 2 waves by each other, or you can multiply a waveform times a scalar. So you can basically gain up a waveform. Multiply it by 2, that's a gain of 6 dB, right? So multiply it by 10, that's 20 dB. So it's really cool. Hey, it's the day before well, day after 4th of July and the day before the weekend, so it's going to get busy out here. So you can multiply two waves by each other, so that's how you do AM. Right? If you want to do amplitude modulation, you can multiply two waves by each other. So you can multiply the carrier, and then you can multiply it by the modulation waveform, which is generally the guy talking on the radio, and you're good to go. That's AM. Okay, some other stuff. Division. Waveform divide. You don't need to go through all that. It works the same way. It's not very common, actually. Here's some other functions. Utility functions. Waveform concatenate. So it concatenates two waveforms together, one end to end, right? So the out wave, in wave 1, in wave 2. That's a way to build a waveform. And a waveform subset. Out wave, in wave, and then you give it the offset and the length, how far you want it to go. And if you use the default values, you basically just get the same wave. But what the default values mean is you don't actually have to specify, for example, the length. The length is assumed to be till the end of the waveform. So you can like remove the first couple of samples from a wave. That's an easy thing to do. And here's an example of generating a waveform. This is a ramp wave. We're going to generate a ramp wave. Waveform generate DC, object, 16 samples, 50 megahertz sample frequency, and 0 volts. So that's just generating DC. Waveform ramp gen 2. Waveform generate ramp, object 256 samples, 50 megahertz sample rate, 0 volt to 1 volt. Boy, I wish I had this back when I was working with analog devices. I had to write my own for this. I didn't like it. And, you know, David does this stuff, it just flies out of his brain. So here we generate a ramp and we have the DC level. Now generally, and I talked about this in other videos, generally when you generate a ramp, you have to be careful because the big drop from the high level to the low level is going to cause a lot of trouble. You don't want to digitize that. So you basically concatenate the DC and the ramp wave. You generate the DC, you generate the ramp, and then you do a waveform concatenate object, temp, and object. So there we go. We concatenated the ramp with the DC offset, and that takes care of that big overshoot problem you have when you go from a ramp straight down. You got a lot of stuff down there. You need something to smooth it out, and so you wait for a while. So that's how you do it. If you want to create your own waveform, you can do this. Waveform set R rect. Waveform object, constant double array. That's an array. Waveform, blah, 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 blah. And give it the units and the increment. Then waveform set R long. So you can create your own waveform if you want to. And what sample by sample, just do it in a loop. Like here's an example of doing a DAC test wave. So waveform DAC test ramp, int I samples 264, long DAC array 264, for I equals 0 through I equals or less than 8, I plus plus. We set the DAC array element I to 0, and then for I equals 8 to I is less than samples, I plus plus. DAC array element I is equal to I minus 8. And then waveform set our long object, samples DAC array, blah, blah, blah. So there, I just created a waveform, and I put it into a waveform for the Nextest. So that's really beautiful. So that's the kind of thing you could do on a Nextest. And, you know, that is DSP. That's what I'm talking about. You do all those functions, you write code in C or C++ or whatever, Python, whatever. We were just watching a thing on COBOL. COBOL is still common. I have written in Forth, which is version of Fortran. So you can do some pretty cool things in any language. You know, I used to think that, you know, I could learn one language and never ever learn another language. I was so wrong. I learned Pascal, I learned the indirect command language on the PDP-11, I learned C, I learned C++, I learned Perl, I learned all kinds of things. I've done lots of languages. You can learn almost any language. There's no limit. So it's pretty cool. You can do a lot of things if you have a brain. If you don't have a brain, well, I can't help you. I can't I can't take part of my brain out and give it to you. Sorry about that. Anyway, so it's July 5th. We're going to get going. Have a nice day. I'm sitting here roasting in the sun. So once again, from the river, this is Dan Bullard. See ya.